Hey, and welcome everybody to Coffee with Clusterone. Yeah, thank you all for joining this morning. My name is Sven, and I'm the growth marketing lead at Clusterone. Yeah, I'll be your host for today. This time we have an exciting guest. Henrik Ek is a senior lecturer for computer science at the University of Bristol in the UK, and he's also a docent in machine learning at the Royal Institute of Technology in Sweden. His research focuses on the theoretical concepts and underlying field of machine learning, which is also what he's going to be talking about today. Yeah, the talk, as you might know, is titled Free Lunch, What Allows Us to Learn from Data. And Henrik will be peeling back the upper layer of machine learning yeah, look at the fundamentals of what it really means to learn from data. So this webinar will last about 1 hour, and we'll be welcoming your questions throughout the presentation. So if you have any questions, if there's anything that you want to know more about, or that you think is unclear, go ahead and type it in the chat, and then I'll put the question to Henrik, and we'll try to answer all your questions. So please, we want to make this as interactive as possible. After the webinar, we'll also send you an email with the slides, and we'll also be recording this session. So afterwards, we'll send you a link with this talk on YouTube. If you want to follow along with the slides, Henrik posted the link in the chat all the way at the bottom, all the way at the top. But as I said, we'll also send that to you afterwards. Yeah. Before I give the stage to Henrik, allow me to take 2 minutes to tell you a little bit about what we're doing at Clusterone. So at Clusterone, we're on a mission to scale AI. We're a deep learning platform that allows you to run your machine learning and deep learning code on a distributed machine without all the hassle of cluster management, infrastructure setup, and so forth. So yeah, Clusterone runs on systems of any scale and any infrastructure. So no matter if you're using AWS, GCP, Azure, or any on-premise installation, we can run on that and support that. Yeah, Clusterone was founded in October 2016 by graduates from Stanford and UC Irvine, and also from researchers from Google X. We launched our product August last year, and in December received funding from the Allen Institute for Artificial Intelligence. Our headquarters in Seattle, so if you want to come say hi, please do. We also have offices in Palo Alto and in Poland, as well as in Canada. So how can Clusterone help your business? Well, we accelerate your business by providing easy access to scalable deep learning infrastructure and to distributed training. So you'd be able to scale your models and train your models faster. Yeah, there's zero DevOps involved, so we take all the setup and maintenance out of your machine learning project, so you can just get to work and solve the problems that you're actually there to solve. We'll also provide total infrastructure freedom, so we support all the infrastructure that you already use. So as I said, AWS, GCP, and so forth, but also if you're switching from one infrastructure to a different one, the Clusterone interface will still look the same. You can just continue working the way you did without having to learn a whole new environment. So this is a quick, very high level, icon-heavy overview of our platform. As I said, we support a bunch of compute infrastructures and storage and artifacts infrastructure. We're sort of the operating system on top of that, so that does all the job management, the orchestration, and so forth. We then provide interfaces and so that you can interact with, but also that a bunch of frameworks can interact with. So we support all the major machine learning frameworks. So using TensorFlow or PyTorch or Keras, we have all those nicely containerized and optimized to run on the machines that you're using. Yeah. If you want to reach out to us, please do. Send us an email, send us a message on our website. We have Zendesk there hanging out, so you can definitely do that. But yeah, now it's time for me to pass over the mic to Henrik and to this exciting talk. Henrik, the stage is yours.
Fantastic. Thank you very much. So to begin with, I am going to try and share my screen to see if this works. And I'm waiting for a thumbs up, and I got that there. Fantastic. This is a first for me, so I'm going to try and give a talk when I have no idea of who I'm talking to. But to begin with, I thought the nice thing to do is to present yourself, right? So if I can move the slides. So I'll start with some introductions. So I live in Bristol, which is in the southwest of England. And that's where I live, and I work at the university. So what do I do? Well, what I actually do is that I ride bikes. This is my dream bike. It's a Colnaglo Master Extra Light. You see the beautiful straight top tube and the chrome straight fork, completed here with a Super Record Campagnolo group set. All Italian beauty. I do not have this bike, but it is my dream. So in Bristol, you can go north if you want to cycle, and you can end up in Wales. And one place I often go to, I've pointed out here, which is Port Talbot. In Port Talbot, there's a steel mill. And I usually go there because just as steel workers, cyclists eat a lot. And there's a very nice cafe there which serves very much food. And then another route you can go is you can go to the south and you can go to Exmoor. Exmoor has, among other things, the steepest road in the UK, and cyclists like to climb, so that's where you go and test your legs. So one day I was down here where the marker is in Lynmouth, and I had a look across the Bristol Channel. So I looked across the channel, and then I saw the steel mill in Port Talbot. Interesting, I thought. It's quite a far way across the Bristol Channel. And when I came home, I opened Google Maps, and they have this very nifty tool where you can measure stuff. So I measured the distance across here, and it's 49 kilometers. And I thought, interesting. I wonder how much the Earth actually bends over 49 kilometers. Now it turns out there's a very nifty app to do this. So I put in my numbers, and it turns out the horizon at 49 kilometers should be 6.2 kilometers away. If I'm standing at 3 meters over the water, and that means that the hidden height of what's hidden behind the horizon at this distance should be 125.6 meters. Interesting. So I had a look at this image again, and then I went to this website, which is called Tall Buildings. And you can actually get how tall the chimney that is at the bottom left if you look very closely. Turns out that that is 135 meters. Interesting thing is, you can also see these small houses around there. They're definitely not 125 meters tall. So I shouldn't be able to see this. This is not possible. So this was severely disturbing for me. It really challenged my ideas and beliefs about how I think about the world. Until it all became clear to me. I've been living and buying a conspiracy. It turns out that the Earth is flat, and this was clear proof of this. Not only did it explain this thing, it also explained why I could see the lighthouse in Weston-super-Mare. And more importantly, it finally gave me an explanation why there's no dinosaurs in Exmoor. Because clearly what happened is very simple. A meteor hit our plane, and then the plane tilted and all the dinosaurs fell off. Fantastic. Okay, so now it's early morning for a lot of you, and you didn't expect to wake up to see a bearded man talk about the flat Earth. So what's this all about? Well, apparently a friend of mine told me that a good talk in statistics contains 3 things. It contains a joke, a theory, and the theory is not the joke. So what I've explained to you now is the fundamental concept of machine learning. What I've just said is what's usually referred to as the no free lunch theorem. And that is what we're going to dig into a little bit here in the beginning. So this is often something which is just thrown out. Your first course in machine learning is going to talk about the no free lunch, and we all nod our heads and say that's obviously true, and then we don't really think about it that much more. And I think it's important to go back to this absolute fundamental core of this thing. So what does the no free lunch actually mean? Well, the name comes from the fact that I think it's in the 30s in the US, pubs were not doing particularly well. So what they said, they advertised, well, the beer's not free, but you get free food if you come in. And then, as all good food, it contains a ridiculous amount of salt. So you ate lots of salt, and what's better to drown that with beer? So then you bought lots of beers, and they earned money anyway. Okay, so what does this mean for machine learning? Well, what is machine learning? Well, machine learning is what we can think of as inductive inference. And this is different from deductive, meaning that what we actually do is that we go from something specific to something general. We see observations, we see data, we try from that data to build some form of generalization or some form of theory that makes us able to reason about the world, right? Okay, so let's try and make this even more specific now. So in machine learning, most scenarios will look something like this. So we have a sample set, some data that I've observed, S. So here I've given these as tuples, X and Y. We can think about this as a supervised setting where X is my input and Y is my output, but an unsupervised setting, you will just have one. Then I have a space of hypothesis, F. You can also think of that as a space of functions, which is where I'm looking for my solution or my generalization, if you want. And then I have a learning algorithm, and this learning algorithm, the task is to search this space, traverse this space of functions. And then finally, I have a loss function L. And the loss function L takes an instance of an hypothesis which has been found by the algorithm A on a data set S. So A, F, S. And then it evaluates that on some new data. Okay, so this can be a classification error, for example. So what we now want to do when we do machine learning is that we want to somehow find a good hypothesis. So what would be a good hypothesis? How do we actually classify that? Well, the sensible thing would be to try and find a hypothesis that would minimize my expected error on all possible data. So that would be an expectation of the loss, which would be, in this case, then an integral, where I take all possible data values that I can have, I evaluate them under the loss, and they're weighted by how likely they are. Great. I think we can hopefully all agree with this. So now the first thing here is interesting, is that the data distribution. So here, let's call this the data distribution. It's some data, some distribution. It looks like this. If I had access to this distribution, everything would be trivial. I've just solved the problem, right? If I know exactly how data behaves, well, I don't need to do any learning. This is the ID. This is what we want to achieve. So what I actually have is that I got samples from this distribution. So I got a discrete number of samples. So say if I got these two samples, it's probably not particularly sensible to try and learn because it doesn't describe this distribution particularly well. So I need a couple of more, potentially something like this. Now I can say that this distribution is potentially well described by these samples. Okay? So now, as I don't have access to P, what I have to do is that I have to take an empirical estimate of this. So what I say is that I take the data that I actually have and I evaluate it under this. And now, this is when things becomes tricky. Because what I can actually now do, I can come up with a data set, for example, that gives me a zero error on the data that I have, but it's arbitrarily bad on everything else. So for example, where I started off of saying, well, the Earth is flat, it's a fantastic explanation for loads of things. It's a really good explanation why I could see that steel work. But if I then try and explain the magnetic field that I can see, it's a really, really bad explanation. And this also goes, and this is what we really call the no free lunch theorem. What this means is if I have infinitely possible number of data, so I have an infinite sample space, but I only see a finite set of data from this, it's possible to come up with a combination of data set, algorithm, and hypothesis space that gives this error just an arbitrary value. And this is the no free lunch theorem. So what do we do in terms of machine learning? What do we actually need to do? Well, we need to make assumptions. We need to take this possible space of solutions and we need to somehow say, well, I prefer these more to something else. If I don't make any assumptions, it's not possible to learn at all. The first assumption that I made, which we often most always do, is that the training data that I will see is somehow well describing the problem. I've got a well sampled data set. But we also need to make assumptions about the hypothesis, so F, and potentially about A in order to be able to proceed. So more specifically, if you formulate, there's many formulations of the no free lunch, but what it really means, this is a definition that I like. We've dubbed the associated results no free lunch theorems because they demonstrate that if an algorithm performs well on a certain class of problems, then it necessarily pays for it with the degraded performance on the set of all remaining problems. So what this really means is that machine learning or learning is a zero-sum game. It's what Donald Trump thinks economy is like. It's a zero-sum game. It's not, but machine learning actually is. And obviously, in order to proceed then, in order to choose specific things, we need to make assumptions. So this whole talk can also be summarized by this XKCD comic, if you want. Okay, so we're now going to talk about assumptions. Assumptions are the thing that allow me to select certain explanations that I prefer compared to something else. What this also means that if you have an algorithm or a model that performs really well on something, the only thing you can say, this algorithm isn't better than anything else. The only thing you can say that the assumptions implemented by my algorithm is better on this specific data set than something else. And it's really, if something solves a problem, it does implicit assumptions, and those are the ones that we should reason about. So assumptions often have a bit of a negative connotation. If you get accused in a discussion of saying, well, you're just assuming this, it's often seen as a weak argument. Another word that we can use for it is beliefs. And I think beliefs potentially have a more positive connotation. And I think the sum of our beliefs is the things that actually becomes knowledge. It's how I am able to act in a world that is not known, right? I take my beliefs and I work according to them. So as another thing, as we're doing machine learning, we've got data. So how does data and assumptions or belief actually interact? Well, if we look at this graph, if we look at the x-axis at the far right would be, I have seen all the things that can possibly ever happen. In that case, I don't need to do any assumptions whatsoever. I don't need to learn. The only thing I need is a method that enumerates everything that will ever happen. On the other end of the scale, I have seen no data whatsoever. I've never seen anything. That means the only way I'm able to act is that I need very, very strong assumptions. And machine learning somehow glides along this thing. Certain methods are really good using massive amounts of data, therefore they need less assumptions, and vice versa. And we're going to come back to this graph. Another way, more traditionally, how this is explained is as this pyramid called the DIKW pyramid, where we say that in order to reason, if you're really, really wise, you need to see very, very few examples. But if you're really, really stupid, you need a lot of data, right? That's one simple way of looking at it. Okay, so let's come back to assumptions then. So we have this object that we were looking for, AFS. So you can make assumptions about your algorithm, A. So basically how you traverse, how you move in the space of hypothesis, how you search it. So this is interesting, and this is a lot of what's happening in the deep learning community at the moment. So I think this is rather interesting. So one way I think about this, it's like I know that there's certain solutions that I don't want. So I want to tell my algorithm to not find certain solutions. So you can think about that like putting an eye patch on your algorithm so that it just doesn't see certain parts. And then we know, and we especially know this with deep learning, is that what we're looking for is these big shallow minimas. And we often find them by, for example, doing stochastic gradient descent. One way of thinking about that is like you put really big clown shoes on your algorithm. So it simply doesn't fall down into the small minimas. It simply cannot walk in there. And then we end up adding things like early restarts, and we do annealing schemes and so forth. And now this is starting to look like Monty Python's Ministry of Silly Walks. But this is really what's happening. A lot of this is how we are training neural networks. And this is really hard, and this is why it is a lot an engineering discipline. It's really hard to explain how this works, and therefore we learn it by intuition. Okay, so another thing is to think about how can I make assumptions on my hypothesis space. So if I have this space of functions, how can I think of how I can place assumptions on this? And this is what most part of this talk is going to be about. So one thing that usually gets mentioned and thrown around a lot is Occam's razor, because what we often say is that, well, we all know that we have multiple, given a finite set of data, we've got infinitely many explanations that can explain it equally well. So then we just choose the simplest. But the simplest also needs to be defined. What is simple? And to me, Occam's razor is an effect of an assumption. So we make certain beliefs, we believe some there and there, or what we believe are the same. Okay. So now comes the next thing. So if we then believe in that assumptions are possibly something that we need, how do we quantify them? How do I actually parameterize assumptions? And one way is to parameterize them using probability distributions. So this is an interpretation of probabilities as a quantification of uncertainty or a degree of belief. So that means this has nothing to do with the frequency. It simply means if I got an input space X, the density that sits over this is how much I believe in X taking this specific value. Okay, so I'm going to summarize this first bit about statistical learning before we move on to the next. So the key things is that there's an infinitely many equal explanations of a finite sample from an infinite sample space. That means we can only ever learn by choosing an explanation based on our assumptions. You can falsify, but never prove your assumptions. So inductive reasoning can never ever be proved right. Anything that you learn can only ever be reasoned about relative to your assumptions. Okay. So with that, I'm going to go on to talk a little bit about what I do research in, which is about how we can parameterize beliefs about functions. So then I'm going to start with a quote. So a book that everyone should read is Judea Pearl's book, The Book of Why, that came out this year, I believe. And in an interview, he said something about machine learning. He said, machine learning is nothing but curve fitting, but it's amazing what you can do by fitting curves. And I fundamentally agree with this. We are anthropomorphizing this field and call it intelligence and so forth. I don't think we are remotely doing anything similar to that. But what we're really doing is fitting curves. And it's really cool. Fitting curves is really cool, and the amazing things we can do with it. So we're going to look at how we can fit curves. So let's think about this space. This is a snapshot of an infinite plane. And what I want to do now is that I want to specify some form of distribution or some form of belief on this space of functions. So this is a bit tricky. So one thing that I can do is that I can think, well, I can put lines, right? Lines have two parameters in this space. So I can put now a belief on the parameters of the lines. Well, that's two. Say that I want polynomials of degree 42. That would require 42 parameters. And those are two very different spaces. So it's really, really hard to specify a general function. So let's move back a couple of steps and just think about functions. What are actually functions? Let's do this. Let's draw a slice along this space. So let's look at the function here at the slice x equals to 3. So this slice goes from positive infinity to negative infinity. So what I know about all functions is that all functions has to cut this line once and only once. Otherwise, it's not a function. So what I can actually do is that I can possibly quantify my belief in where I think the function cuts this slice. So let's now say that I specify that belief to be a Gaussian. So if I now do this, the interesting thing with this is that the Gaussian has infinite support. So at positive infinity and negative infinity, this distribution has a non-zero value. That means I haven't excluded a single hypothesis or a single function or a single intersection. I've just placed a preference that in this case I think they're close to 0. Okay? There's nothing special about 3. So if it's true at 3, it's probably true at -2 as well. And actually, possibly everywhere, right? So now the question is, how many of these slices can I draw? Well, it's an infinite space. So I can actually parameterize it like this. I can actually write down a function that says that the variance of each slice of this Gaussian is a constant. Cool. Well, that's really nice. Okay. So what more do we know about functions? Well, the next thing is any interesting function, at least, is if I would now go back to my two friends, -2 and 3, say that if I would know the value of the intersection at -2, well, I don't really trust my data, so I have a little bit of slack around it. What does this actually say about the value at 3? Any interesting function would have some form of interaction between these intersections, you would believe. Well, either you can say, well, actually, if I know the value at -2, it doesn't say anything about 3. So I go back to the belief that I had before. Or I can say, well, actually, if I know the value at -2, it's exactly the same. So my uncertainty, my belief is just transferred. Or more probably, it's somewhere in between these. And the way we're going to get this behavior, this is the behavior that we really want to specify. This is how we're going to try and think about functions. We're going to think about functions as how these slices interact with each other. And the way we're going to do that is saying that both of these slices are jointly Gaussian. So rather than thinking about these one-dimensional slices, I'm now going to think about a two-dimensional Gaussian. So in the beginning, I said we can specify, when I had this tube, I can say that, well, I can write that as a function, the variance. That's the diagonal elements of this. Now the cross terms here is my covariance elements. And this distribution that I'm showing is now the distribution, the joint distribution of the intersection at x1 and the intersection at x2. So the values of the function there. And now, if I say that I know the value at x1 being a half, I now get a distribution over the value of the other one. Dunk, dunk, dunk. And that is a Gaussian process. So now we can write down the definition of a Gaussian process is an infinite collection of random variables whose any subset is jointly Gaussian. So what this really means is that I have an x-axis. I can take infinitely many slices. Any slice that I take, the collection of where those outputs are jointly Gaussian. And that's it. So now, the way we parameterize the covariance, so saying how much information from, in this case, -2, how much information knowing the intersection value there, what does that say about 3, is this off-diagonal elements, the covariance. And we can do that in many ways. We are going to do that using a function which only depends on the input location. So the value of the output location depends on the input location. That's kind of the definition of a function. So now one way of saying is that, say that I now know -2, 3, and 6, I can say the further away I am from the value that I know, 2, the less I know. The less information, the less informative the value at -2 is. That would be a smooth function. I can also say, well, actually, I have some periodic behavior. So say I got my index space is actually time. So over time, I know that Tuesdays and Tuesday next week, they kind of co-vary with each other. So now I can write a function that used to have a periodic behavior, and I'm going to get a periodic thing. Excellent. So what I now can do is that I can write down and take any finite subset of this. So let's, for example, say that I take 100 values along this x-axis. Now I compute my covariance function, which gives a 100 by 100 matrix. It's a 100-dimensional Gaussian. I draw one sample. This sample is going to be a 100-dimensional vector. I plot those values with its corresponding y values. If I do that, I get something that looks like this. So this here is a couple of samples from this function. And importantly, this space here, these functions, contains all possible functions. It's just that my preference have been encoded in this covariance, so certain ones I believe in more than others. Fantastic. So with that, I'm just going to say cheers to Gaussian processes. And actually, come to think of it, beer is an excellent continuation of this explanation. So, if I should explain to you how this beer tastes, I can either give you a parametric explanation of beer, which would be, I would give you a recipe, right? I would tell you exactly how much malt, what kind of barley, what kind of hops, and so forth. That would be what we call a parametric model. Another way of giving it is that we've all drank a lot of beer. So if I can find some beers that we all have drank, then I can say, well, actually, this Newcastle Brown, it has the maltiness of this beer and the hoppiness from this, and it's a little bit in the bitterness of another. That would be explaining the taste relative to something else. That's what we call a non-parametric explanation. And I think as soon as we look at complicated explanations, this is really how humans function. And this is exactly how I define the function. I define the function in terms of how do function values vary, not on how it is parameterized. Okay? I hope this makes sense. And there's a whole class of functions which are non-parametric, the easiest one clearly being a nearest neighbor. Okay, so now comes the really, really cool thing about this, why it's so simple. So Gaussians have this really, really cute thing that Gaussians are closed under multiplication. That means if I multiply two Gaussians, I get another Gaussian out. So say now that I've observed some values f. These are the output values of the function. And now I want to see what some other x values, what the function could be. So now that's a joint Gaussian again. Fantastic. And now I can write down, so P of f comma f star is just my Gaussian distribution, where I don't know some of the f stars. And what I really want is f star given f. Well, now I know that P of f, that's just writing down another subset. I can also write that Gaussian down. And because I know now that the product of these two things generates a Gaussian, the thing in the middle, the conditional distribution, has to be Gaussian. This is really, really cool. So I can actually derive that one in closed form. The only thing you need to do is identify the parameters of this and make it, and identify the parameters of a Gaussian by completing the square. If I do that, what I actually get is this big object here. It looks a bit complicated. It isn't. It's just another Gaussian. Importantly, it's actually another Gaussian process because, again, it's defined over an infinite index set. The cool thing about this is that I've effectively done base rule in closed form. By completing the square, I've computed the integral in base rule. If I look at that, what I've really, really done here is that I've taken my prior, which is the leftmost plot, where I've said these are the hypotheses that I like, and I give them different weight. I see a data point, and I put 0 probability on all solutions that don't agree with my data. Right? So this is exactly seeing one data point and removing everything that doesn't agree with that in my prior. And now I have my updated belief. So this, I think, is really cool because I just did that with some simple interalgebra. Okay, another way of seeing this, which leads to one of the biggest uses of these things, is this. So let's say that I have this red function. I haven't seen this function. I don't know this function. And now I have a prior over this function, which is this blue thing. Initially, I haven't seen anything. So now what I'm going to do is that I'm going to continuously start seeing points, and you can see how my belief is updated. So I see this point. You can see now I become more certain around just there. I start seeing points, dunk, 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 and I start learning something about the function. So this here, you can now think the uncertainty here, the assumptions, the beliefs, my updated belief that I get through this can be really, really useful. So say, for example, that I would like to find the minimum of this function. So I would find out a sensible way to search this function in order to find its minima. Well, I can now use this uncertainty to balance an exploration versus an exploitation phase. And this is the foundation of Bayesian optimization, for example. So I'm going to click this through and dunk. Now we ended up there. Dunk. Okay, so now that was what I actually was going to talk about in terms of Gaussian processes. And now I thought I'll talk about something else related to this, namely composite functions. Because if you're doing machine learning these days, you have to use those famous 4 letters, deep, because that's what the kids are doing, and that's all the rage at the moment. So I don't like using that word. I think it's a nonsense word, because actually mathematicians have been doing this for a very, very long time. And if you open your first book of calculus, you will see them mentioned as composite functions. Because actually, what is a deep neural network? It's a function in a function in a function, right? That's it, right? It's a peculiar type of function, but it's still just a function in a function. So now, rather than calling them deep, we're going to call them composite functions. And there's lots of work on this. There's limit proofs, for example, which is really exciting. Okay, so how does everything I've talked to in terms of assumptions relate to composite functions? So the first thing that we will know about composite functions is that a characteristic of a function is its kernel and its image. The kernel is the number of values in the input that maps to the same value in the output. And the image of a function is all the values that the output contains. Okay? So if I now put a function in a function, some interesting things happen. Because as soon as my function is non-monotonic, so the function on the left, in this function here, -1 and 1 are two different values. Oh, I shouldn't be doing that. Two different values, and they map to the same point, right? So that means those 2 points are collapsed. So that means they now go to the kernel. While the image now shrinks, because these two could have been mapped to two specifically new values. So when I compose by adding layers to a function, the only thing I'm doing is that I can only ever increase the kernel and decrease the image. So if I add layers, I'm decreasing the representative power of my network. And this is rather counterintuitive because it feels like you're adding parameters, but you're actually reducing the possibilities of what you can represent. And this is true for non-monotonic functions. So if we then look at, on the right plot, we look at the typical activation functions people use. If we look at the sigmoid, that is actually a monotonic function, but the gradient changes very much. So in one region, it's very, very flat. So all those values along the x-axis are pretty much going to map to the same. For a ReLU, the green one, actually all those values, the negative values, maps to the same point. So you collapse this whole part of the space. They all become part of the kernel. Okay. So this is actually really cool and really useful. But let's go back to thinking about this in terms of distributions. So let's say I got a space, 0, 1, and I place a uniform distribution over this. So I think everything in here is equally likely. Now I'm going to push this uniform distribution through this red wiggly line. So as you can see, what this does, it first compresses the space, then stretches it, compresses, stretches, and so forth. If I do this, it's going to look like this. I get these bumps out. Cool. Now, for the sake of interest, I'm going to say we're doing a classification task. So I'm going to say that 2 of these bumps are class 1, say that they're cats, and the other 3 are dogs, right? Now, this is quite hard to classify, right? So what I'm going to do is that I'm going to push this through another set of functions. I'm going to push it through this type of function, which is very much like a set of ReLU units. Now, if I do this, I'm going to end up with 2 bumps, because now I've pushed my kernel and I map 2 of these, the cats to cats and dogs to dogs. Great. Actually, that image is a bit of a lie, because what I actually have is something like this. I've mapped this thing to basically 2 delta functions. Cool, this is exactly what I want. This is super easy to classify. I've taken the whole real line and mapped it to 2 points. Great, and these points are cats and dogs. But also, what we need to think about, what has happened to the probability mass? I only have 2 values of the probability. As soon as it's within a delta function, which is the only place it can be, I'm equally certain of everything. And now if we go to the leftmost plot, if I move slightly along the x-axis between 2 of these bumps, my output changes that I'm jumping between the classes. And I am equally likely. I can't differentiate this with my belief. And this is really why these things are so brittle. They're really, really brittle because you have this effect of collapsing the space, right? Okay, so often machine learning is explained through this interesting graph. So this says that what we should be doing when we select models to avoid overfitting is that we should look at the marginal likelihood. We should look at the probability of the data that I've seen. So if the probability of the data is on my y-axis, and on the x-axis, I have the data somehow sorted according to complexity. If I now have data at d0, and I have 3 models which places probability mass in these different places, the model that I should choose, the model which is the highest according to P of D, is M2, because it places probability mass just where it should, while M3 explains too many things and M1 explains too few. There's a great plot that David Mackay did, and here it's stolen from Chris Bishop's book. But actually, this plot doesn't make any sense whatsoever with composite functions. Because what a composite function actually does is that every layer until the last is reshuffling the x-axis. So what it does is that it takes all the data points, it puts all the data points as close together exactly at x is 0, and then a really simple model can put probability mass exactly there. So this means this argument kind of falls. So then the next thing that I wanted to come to was priors. So we talked about beliefs about the functions that I think I want to have in a network. So let's say I got this very, very simple network with 2 layers, and I say I like periodic functions. So say that I have a prior that really, really likes sine functions. If I like sine, I probably like phases of sines. I probably like cosine. Now if I map a sine through a sine, I get the red curve. If I map a sine through a cosine, I get the blue curve. These 2 are fundamentally different. The period had changed. They changed brutally. So what I'm trying to come here is use the idea that if I specify something which is natural on each layer, it often becomes really, really strange when it comes out at the end. So we can't really think, it's very hard to think of priors as decomposed in compositions. My last tricky thing is the composition of uncertainty, and I should hurry up a little bit. So here, let's now think about what happens when we push uncertainty through compositions. So let's say I have a line here, it's an identity function. And then I add some uncertainty around this. I'm not really sure about where it goes, so I have a tiny bit of uncertainty. And now I push that through a sine function. So that would mean I wiggle, I move the x-axis like this. And if I now paint out this uncertainty, I'll get this thing here. But I'm also a little bit uncertain about the sine function. So now I have to add uncertainty to that. And now I push that through, I'm going to end up with this. And now what I've effectively done is that I've taken these small parts of uncertainty and I ended up with this, which we probably think is quite uncertain. And this is simply because the way we're thinking about uncertainty is often in this thing which I started off when I argued about Gaussian processes. We take a slice of x and we say, what are the possible y values here? And these y values here would be terribly uncertain. So if I would use that to fit to my data, it wouldn't make any sense at all. It would be really, really hard to fit. But actually, if you would draw samples from this, all samples would look very much like sine function. They would just be slid along like this. So it's actually very, very hard to use the uncertainty if you propagate these things through. So how do we actually deal with these things? Well, the way we seem to be dealing with these things in most cases is that all what I've said in the last couple of slides on composite functions is that they're really, really hard to think about. That means it's really, really hard to make assumptions, which means it's really, really hard to have beliefs about them. So that means I can't be on the left side of the scale and I have to move really, really far to the right. The only way I can do this is by increasing the amount of data that I need. And to me, this kind of explains the negative side of composite functions, that I need to deal with enormous amounts of data. And so to summarize this, it's not really a criticism of neural networks. It's a challenge of composite functions. Assumptions are hard to make, and this forces us to use these massive amounts of data. And also, it forces us what I said in the beginning. It's really hard to make assumptions about the hypothesis space. So therefore, I make assumptions about the algorithms. And these are really, really hard to interpret. It's really hard to formulate explicitly what assumptions these implement. And that means I can't communicate them. And knowledge, to me, is assumptions that have been written down in explicit form. So this, to me, is the big challenge of these things, and I hope more people should be working on these so that we can actually try and understand these. Right, so now I'm just going to conclude a little bit. So I hope you've enjoyed this, and my main argument here is just like, don't forget the no free lunch and think about what it actually means. As soon as you read a paper which says we've removed lots of assumptions and we're getting better results, that's wrong. Then your reply should just be, wow, you've broken the no free lunch theorem. That's fantastic. Because as soon as something works, that implies that assumptions have been made. And often we try to hide them, but rather the best possible work is the work that says, I've made loads of assumptions and they all work. That's great. I usually use the example of a football player. I'm absolutely awful at football. I'm Swedish, so I'm allowed to talk about Zlatan Ibrahimovic. So Zlatan Ibrahimovic is much better at football than me. Why is he better? That he makes assumptions, and he makes relevant assumptions. Put me on a football field, I assume that the ball could come from any possible direction and anyone can do anything. While Zlatan Ibrahimovic has a really, really, really narrow probability distribution over the things that are going to happen. So his reasoning becomes simple. Mine is all over the shop. There's a couple of other things that makes me worse in football as well. But so the last thing, inductive reasoning can never lead to truth. This is very, very important. We can only argue, it can only be true relative to my assumption. So in the end, that's kind of what I wanted to get across. And the way I talked about Gaussian processes would use one way of thinking of old classic models that allows us to make very, very fundamental and clear assumptions about problems. We have different challenges, but at least my assumptions are very clear. And with that, I think I was going to end. Fantastic.
Cool. Thank you very, very much, Henrik.
Oh, thank you. Now I can continue drinking my beer.
Yeah. So we do have a few questions that.
Oh, fantastic.
So I'm just going to put the first one of those to you. So somebody asked how you would formulate causality learning in terms of statistical learning.
Oh, wow. Oh, fantastic. This is so hard, right? So causality is incredibly hard, right? It's we're not doing it. No one's doing causality. So the interesting thing is that when we specify these probability distribution, we specify conditional distributions. Conditional distributions are not causal. They're just saying, this is what I can say about one object given the other. And Judea Pearl and his group have been working on these things which they call a do notation, which is basically notations which are directed. It's basically like thinking about conditional distributions, but you can't flip them around. And the only way I know is to basically try and do these statistical tests to try and figure out. But I'm not an expert on this, but causality is obviously what we want to do, but really, we're not even remotely touching on it. One interesting thing is that I think you should test this with your own heads. A lot of the time we think causally, but we write down code and models and we think about them causally, but they never are, right? So sometimes we make reasonings which are not true. Okay, how was that for a non-answer?
Thank you. Yeah, so we have another question that is a little more general, and that just asks what you think is the main difference between machine learning and statistics?
Oh, very good. I think they're exactly the same. I think machine learning is a field of statistics. I think we are generally interested in two different things. So I think mainly the use of statistics is to basically, the model is the interesting thing. The explanation is the interesting thing. While machine learning has mainly been focused on prediction. I don't really care what this internal stuff is doing, as long as it always predicts the right thing. My talk here has kind of been arguing that that's actually that's not particularly interesting, right? It's like if I go out here with my flat earth friends, and I don't really have any, I would love to have, but if I go out and look around, I can't disprove them with data. So their predictions are always right? But still, what I want is their explanation, and then I can say that they're wrong, right? So in a way, I think the fields are the same, but they've had a slightly different focus. But I think we should learn so much more of going back to being more proper statisticians.
Yeah, that sounds about good. Thank you. The same person who asked the last question also asked one more question to extend this this question. And what will be the pros and cons in that sense of deep learning or of compositive functions, I guess?
Oh, say that again.
What will be the pros and cons of deep learning in this sense of statistics? Because you said you talked about deep learning a little bit, and then it seems like you said deep learning is a little overrated, or maybe not.
No, well, no. Okay, good. I think I understand this question. So what I meant was that this is what I think machine learning is very, very good at. We are often creating words for new things, which are a little bit exciting and often a little bit anthropomorphic, as I used in the abstract. We're talking about intelligence, please stop doing this. We're doing curve fittings, please stop. But and also deep is another thing like that. It's why do we need to use that word when it's really exactly very clearly defined by mathematicians as composite functions? It's just that it's a much less sexy word, and it seems to be that we invent now all these things wow, this happens with it, and then you can pick up a calculus book that's 250 years old and you can read it there. And I find that a little bit sad, because we are just differentiating things in order to be different. And I think we're losing out a lot on this, because at the moment we're seeing this massive boom. And this is super exciting, right? This is really cool what all these deep learning systems can do. But we are running into a wall with data. And now there's so much that we can learn by actually not differentiating us, but actually realizing, hang on, we're the same as this. What do they actually know? And that, I think, is important. So that's my whole point. A deep model is a composite model, end.
All right. Cool. Yeah, we're basically out of time. And as it happens, we're also out of questions. So this fits perfectly. Yeah, all that's left for me to say, Henrik, thank you very, very much. This was very exciting. There's a lot of praise on the chat of people who think this was a really cool talk.
Okay.
So yeah, thank you so much for doing this. Really appreciate it. To all people attending, we're going to be sending you an email within, this afternoon, within a few hours, with the slides and also a link to the talk, to a recording of the talk. And yeah, if you want to know more, check out our website, clusterone.com/webinars, where you can see upcoming webinars and other things we're doing.
And I can also say one final thing. This was a real pleasure. I really enjoyed this. It was a totally new experience. I wonder what my neighbors think. I've been we got quite thin walls here, so they've also listened, I'm sure. But if you're interested in Gaussian processes and things like this, we just had last week a summer school in this, and there's a website with tons of talks, and it's called gpss.cc. You can find a lot of that there, and you'll see bits of this talk there as well, if you're interested in this research topic. Okay.
Awesome.
Thank you very much, Ben.
We're also going to include that the link to that website in the email, so you guys don't have to like write it down now. All right. Yeah. Thank you, everybody. Thank you, Colin, Henrik. This was great. And yeah, have a great day.
Thank you. Bye-bye.
Bye.